Let's talk about sensors, a new dimension of detection. Let's delve into the core of how we perceive the world. From industrial automation to consumer technology, sensors are the unsung heroes. We'll explore the latest advancements and the challenges that lie ahead. Magnetoelectronics, the material revolution. The heart of tomorrow's sensors lies in the materials of today. Heusler and half-Heusler phases, these intermetallic compounds are a paradigm shift. Their unique magnetic and electronic properties offer unprecedented opportunities for creating ultra-sensitive and energy-efficient devices. Insights from an expert. Featuring the captivating podcast with Dr. Block. Discover the cutting-edge research and thought-provoking discussions that are shaping the future of magnetoelectronics. Brought to you by All About Sensors.
Imagine a future, right, where your electronics aren't just faster, but they're fundamentally smarter. They never lose data, they use less power.
Sounds almost like science fiction, doesn't it?
It really does.
Yeah.
But today, we're actually diving into something that could make it real.
Mm-hmm.
The world of magnetoelectronics.
Mm-hmm.
Specifically, we're focusing on these fascinating materials called Heusler and half-Heusler phases.
Right.
Our mission for you listening is to unpack how these unique compounds might just be the key to next-gen computing.
And we're digging into a really interesting source for this, a 2002 doctoral dissertation by Thomas Block. It's called New Materials for Magnetoelectronics, Heusler and half-Heusler phasen.
Originally in German, yeah.
Yeah, but what's amazing is how relevant Block's vision from back then still feels. He was really focused on finding materials with high spin polarization, high magnetoresistance, basically stuff to revolutionize computing.
Okay, so let's start there. Block talks about spintronics. Now, most of us think about electron charge carrying information. What does using its spin actually mean? How does that add a new dimension?
Well, it's exactly that, add in a quantum property. Instead of just, the flow of charge, spintronics uses the electron's intrinsic spin. Think of it like a tiny magnet pointing up or down.
Okay.
And that spin state itself can carry information. But to make that practical, you need materials with really high spin polarization.
And that's where the Julier model comes in, to measure that.
Exactly. It helps quantify it, linking that polarization level directly to how much the resistance changes the magnetoresistance effect.
So if high polarization is the goal, what's the sort of dream material for spintronics?
The dream. That would probably be half-metallic ferromagnets. Something like Nimmonsby is the classic example.
Half metallic. What does that mean?
It means, theoretically, they offer 100% spin-polarized current. They act like a metal for electrons spinning one way they conduct easily. But for electrons spinning the other way, there's a band gap, like an insulator. They're completely blocked.
Perfect spin filtering, basically.
Theoretically, yes. But, and this is a key point Block already wrestled with, experimentally proving that perfect half-metallicity in Nimmonsby, that's still debated. It's tricky to achieve in the real world.
That challenge makes an older discovery maybe even more surprising. You mentioned Heusler earlier.
Yeah.
From way back.
Oh, yeah, back in 1903, it was really quite something. Heusler found that certain alloys, like manganese and copper, which aren't ferromagnetic themselves,
right, non-magnetic,
could actually become ferromagnetic when you mix them with other main group metals. Think about that, making magnets from non-magnets.
Wild. So these are the Heusler and half-Heusler phases.
Those are the ones. They're intermetallic compounds. But sometimes they show weird properties, like being brittle or even semiconducting, like nizarsen.
Which isn't typical for intermetallics.
Not always, no. It points towards strong covalent bonding, which turns out to be useful for electronics.
And these compounds, they've really driven progress in data storage through magnetoresistance, or MR effects. Let's talk GMR.
Giant magnetoresistance. Yeah, that was huge. Discovered 86, and by 97, IBM had it in their hard drive read heads.
That's incredibly fast.
It was. It totally changed the game for data density. I think terabyte drives GMR paved the way. It works because the resistance changes massively depending on the magnetic alignment in different layers.
And building on that, we got TMR.
Right, tunnel magnetoresistance. This is the foundation for MRAM, magnetic random access memory.
Which promises memory that doesn't forget when the power's off, unlike DRAM.
Exactly. Non-volatile, fast, tough, energy efficient, potentially replacing DRAM someday. Block even talked about using TMR for new kinds of circuits, like spin transistors.
So GMR, TMR, what about CMR, colossal magnetoresistance?
CMR. You see that often in materials called manganites, but Block highlights this record setter, GDI2, gadolinium diiodide.
And what was special about it?
It showed a massive 70% change in resistance MR0 effect at room temperature, though you needed a pretty strong magnetic field, 7 Tesla.
70%. That's, well, colossal.
It is. But there was a catch. GDI2 is really reactive. Air, water, doesn't like them. Plus, it wasn't very sensitive to smaller magnetic fields. So, great science, but hard to use practically.
A common story, unfortunately. So given all these materials, some promising, some tricky, how do researchers actually design new ones? Block mentioned an electronic fingerprint.
Yeah, they look for a specific combination of features in the electronic structure. First, a saddle point, which gives a high density of states, lots of electrons available at a certain energy.
Okay, a saddle point.
Then a tendency towards spin density wave instability, and also a local magnetic moment. It's this complex magnetic interplay they think causes the big resistance changes.
And Heusler phases fit this picture well.
They're great candidates. Because they're so adaptable, you can tweak them atom by atom using doping to fine-tune their electronic properties, the VEK, or electron concentration.
VEK, Valence electron concentration. Trying out my German.
Exactly. And crucially, they often play nice with existing silicon technology. You can grow them epitaxially, like Co2N-Ing on gallium arsenide, a standard semiconductor wafer.
So, a bridge from the lab to manufacturing.
Pretty much, yeah. That compatibility is key.
One last technical bit. How do we actually measure the spin polarization directly?
Block mentions a technique called Andreev reflection. It's about how electrons behave at the junction between a superconductor and a ferromagnet.
Okay.
Yeah, the way they reflect or get converted tells you about their spin state inside the ferromagnet. It's a direct probe.
So we've gone from a really surprising discovery over a century ago through all this intricate science. Heusler phases, MRR effects, really mapping out the future of electronics.
It's quite a journey, and as researchers get better at understanding and, controlling electron spin, just imagine devices that aren't just faster but truly smarter, running on the quantum nature of matter itself.
Makes you wonder, what completely new things will spin into existence next? Ever wondered how just, tiny tweaks in a material structure can lead to these really mind-bending properties?
It is fascinating stuff.
Yeah, so today we're doing a deep dive into Heusler and half-Heusler phases. They seem like these hidden gems, really.
Holding keys to future tech, definitely. But their behavior is incredibly complex, often surprising.
Right, so our mission basically is to explore this delicate dance between how their atoms are arranged, their electron count.
And how that all connects to whether they conduct electricity or react to magnets.
Or even become these, quantum wonders. And we'll see how tiny changes in how you make them can just lead to totally different results.
Okay, so let's start with a really key concept. Valence electron concentration. VEK for short.
And EK, right, the outer electrons.
Exactly. It's basically the number of those electrons available, and it's a critical indicator of what the material might do.
Okay.
And what's really interesting is finding this sort of magic number 18, VEK. That often points towards semiconducting half-Heusler phases. Cotizib is a good example.
18 VEK equals semiconductor. Got it. So what happens if you, move away from 18? Is it just a small tweak or?
Well, that's where it gets really interesting. Shifting that count can totally transform them.
How so?
Take NiVSB. It has 20 VEK, slightly higher. It becomes a half-metallic ferromagnet.
Half-metallic, meaning?
Meaning it acts like a metal for one electron spin direction, but like an insulator for the other. Really important for spintronics.
Okay.
But, and this is important, shifting the VEK can also start introducing structural disorder. Things aren't perfectly arranged anymore.
And we saw that with PDM&T, didn't we? Much higher electron count there, 23 VEK.
Right. And theories suggested antiferromagnetic.
But it wasn't. It flipped to ferromagnetic at low temperatures. Kind of a twist.
A compelling twist, yeah. And it also showed this really noticeable negative magnetoresistance, minus 15% at 4 Kelvin.
Which means its electrical resistance drops when you put it in a magnetic field. Useful for sensors, maybe.
Potentially, yes.
Yeah.
And what's fascinating there is if you look at PDM&T's band structure.
The energy landscape for electrons.
Exactly. It shows this feature called a Van Hove singularity right near the crucial energy level, the Fermi energy.
Yay.
Which suggests that even a tiny push, a small change, could potentially tip it over into a fully half-metallic state.
Directly influencing that magnetoresistance effect we saw.
Precisely.
So electron count can throw curveballs. But what about when the material itself just doesn't behave like the simple model says it should?
That brings us to Cummins B, right?
And a magnetic mystery.
Yes, Cummins B, 21 VEK, Curie temperature of 478 Kelvin. It's considered a half-metallic ferromagnet.
But the problem is the measured magnetic moment, how strongly magnetic it actually is.
It's about 4.2 Bohr magnetons per formula unit.
Which doesn't match the theory for a perfect structure, which predicts 3 Bohr magnetons. That's a big difference. What's going on there?
It is a big difference, and it's a huge clue. It tells us there must be some significant structural disorder or maybe complex overstructures we aren't accounting for.
Things messing with the perfect arrangement.
Exactly, and that has a profound impact on its magnetic and electronic properties. COM-NSB, for instance, also shows a pretty big negative magnetoresistance, minus 14% at 4 Kelvin.
Okay, so it seems like designing these is like, I don't know, molecular Jenga. A tiny change shifts everything. But can we actually use that, engineer those shifts?
Well, that's the idea behind doping. Consider the series CoV1XMXCB.
Where you swap out some vanadium for manganese atoms.
Right. You're trying to engineer specific fingerprints in the electronic band structure, maybe place those Van Hove singularities right at the Fermi energy.
Because that's thought to be key for colossal magnetoresistance, CMR, the really huge drop in resistance.
That's the theory. And for one specific mix, CoV 0.6 Mn 0.4 SB, which has 19.8 VK, those electronic fingerprints are there.
Okay.
And the theoretical magnetic moment, 1.8 Bohr magnetons, actually matches the measured value quite well. So it seems like we understand this one.
Seems promising for CMR then.
You'd think so. And the literature actually reported a massive CMR, 49%. But in our hands, we only measured about minus 5% at 200 Kelvin.
Wow, that's a huge discrepancy. Why?
That's the million-dollar question. It's a major area of investigation right now. It just shows how incredibly intricate the balance is. Theory points one way, but reality.
Reality can be tricky. And sometimes it's not just the ingredients, but how you cook them, right? The manufacturing itself.
Absolutely critical. Let's look at the Heusler phase, Co2-Krell, 27 VEK.
Okay.
For ages, it was thought to be this perfect half-metallic ferromagnet, 100% spin polarization, predicting a 3 Bohr magneton magnetic moment. But earlier experiments kept finding lower values, like 1.55 Bohr magnetons. Something was off.
So what did you find?
Our deep dive showed the preparation method is absolutely key. If you cool the material really fast after melting it...
Quenching it.
Yes, quenching. You get a magnetic moment much closer to theory, around 2.9 Bohr magnetons. It suggests a more ordered structure.
Okay, so fast cooling is good for order. What about slow cooling?
If you temper it slowly, let it cool down gradually, the magnetic moment just tanks. Drops to 0.8 Bohr magnetons. And its Curie temperature falls dramatically too, from 331 Kelvin down to 200 Kelvin.
Wow. Just from cooling it differently. It's like atomic level baking, isn't it? Change the oven temp slightly and poof.
Exactly like that. And we use neutron diffraction to confirm it. The slowly cooled, tempered samples showed structural changes, specifically phase segregation.
Meaning bits of the material started separating out.
Correct. Different phases forming within the material. And that directly explains the changed magnetic properties. It just highlights how incredibly sensitive these materials are. A tiny tweak in synthesis
Can fundamentally change how they behave. Amazing. So what a journey through these Heusler and half-Heusler phases. It really shows their incredible potential, for computing, for sensors. But it's all hidden in these tiny, tiny details. The atomic structure, the electron count, even just how fast you cool them down.
It really makes you think, if we can get to the point of designing materials with this level of precision, controlling properties just by adding or removing a few atoms, or tweaking the cooling time by a fraction of a second, what kind of completely new technologies could that actually unlock for us down the road?
Definitely something to think about.
Okay, so think about this. What if the next leap in electronics, like in your phone or medical sensors, wasn't about making things way more complicated and expensive? What if it was about, I don't know, unlocking some hidden power in, well, simpler materials? Imagine devices super sensitive to magnetism, but built cheap. Today, we're doing a deep dive into exactly that. A fascinating new material and some really clever design.
Exactly. Yeah, our mission today is to really dig into this paper on a specific Heusler compound. That's a type of alloy known for interesting magnetic properties. This one's called SiCO2PCR and 6-Cyprusia. Quite a mouthful, I know. But we're going to unpack why it's so special, look at the predictive science that created it, and see how it could genuinely shake things up. Think hard drives, spintronics, the works. It's more than just finding a new material. It's about a a smarter way to use the physics.
Right. And the core idea here is magnetoresistance. Yeah. Materials changing resistance in a magnetic field. We use that now, in hard drive read heads and stuff, but those are usually pretty complex systems, like multiple layers. Why is simplifying that so hard?
Well, yeah, you've hit the nail on the head. There are materials with huge effects, this colossal magnetoresistance, things like manganites or DDIET2.
Yeah.
But the catch is they need extreme conditions, really strong magnetic fields, or they have to be super cold, just not practical for most things. And for spintronics, the dream is a half-metallic ferromagnet. It basically filters electrons by their spin-polarized tunneling. The big challenge, finding one that actually works well at room temperature, and critically has a high Curie temperature, so it stays magnetic when it gets warm. That's been the real bottleneck.
Okay, so it sounds like people were kind of searching in the dark for a while, just trial and error. But this team, they didn't just find it, they designed it. How do you even blueprint a material like that?
That's what's so cool about this. Yeah, they didn't just stumble on it. They used electronic structure calculations, like using the physics to predict the perfect recipe. They were looking for specific electronic fingerprints, things like a Van Hove singularity, basically a spike in electron states near the Fermi energy. That's the key energy level. And also a gap, an energy gap in what's called the minority spin channel.
And they found a compound, or rather, they made one fit those specs.
They started with a known Heusler, Co2CrNL, but then, and this is the clever bit, they carefully doped it. They swapped out some chromium for iron, precisely, to get COTCr$6FCl4. This tweaked the electron count just right to 27.8 per formula unit. And that little adjustment, it nudged the Fermi energy exactly where their calculations said it needed to be, really optimizing those half-metallic properties. It was very deliberate.
Okay, the design sounds impressive, but the proof is in the pudding, right? Did it actually work? How good was it, especially compared to the original stuff?
Oh, the results were fantastic.
Yeah.
Really remarkable. This engineered material showed a 30% change in resistance.
30?
Wow.
Yeah, 30% magnetoresistance at room temperature, and get this, in a magnetic field of only 0.1 Tesla. That's pretty small. And just to show the design worked, the original stuff, the undoped co-serial lower, showed basically nothing. Zero effect.
Okay, that definitely proves the design strategy paid off.
Huge difference.
So 30% at room temp, small field. What does that mean practically? Where could this actually be used?
Well, a few things stand out. First, it has a high Curie temperature, around 750 Kelvin. That's way above boiling point. So it stays magnetic even when things get hot, which is great for, say, sensors in cars or industrial settings.
Okay.
And it's not just theoretical. They've already built what's called a spin valve tunneling junction with it. And even in that device, it showed a 16% effect at room temperature. So it's, showing real promise for actual devices.
16% is still pretty good for a real device.
Yeah.
And you mentioned something else, unexpected, an anisotropic effect. Yeah, that was interesting. They found the effect changed depending on the direction. Align the current and field one way, you get a negative change in resistance. Align differently, it flips to positive.
Weird.
It is. It suggests there's maybe some more complex physics going on under the hood that we don't fully grasp yet. It's still got some secrets.
Yeah.
But bringing it back to why you should care.
Yeah.
This material isn't just high-performing. It looks suitable for magnetic sensors made using cheap powder methods. And crucially, it's an intermetallic compound, no oxygen. That makes it way easier to integrate with standard silicon chip technology. Big hurdle bypass there compared to oxide materials.
Right, the manufacturing angle. That's often overlooked.
Definitely.
So wrapping this up, what we've really seen today is this amazing example of designing a material on purpose, taking something relatively simple, polycrystalline, potentially cheap, this COTCR at 2CFVACSV04, and engineering it to give fantastic performance, high magnetoresistance, room temp, small fields.
Absolutely. And it really makes you wonder, doesn't it, if this kind of targeted design, really using the physics predictively, can unlock such practical and powerful magnetic properties. Well, what other breakthroughs could this approach enable? For other technologies, maybe completely different fields we haven't even touched on, what do you think might be the next big frontier for this kind of smart material design?
Thanks for watching. I hope you liked it or learned new things. Please also visit me on X, Instagram, or read my blog articles on WordPress. Bye.